So let's start then. So what we discussed in the last class was what's the importance of linear time invariant systems, and what does Fourier transform do. Basically, it allows us to predict the output of a LTI system. Any input, because of Fourier, we can represent in terms of sinusoids, and an LTI system will give the same sinusoid as output with its amplitude uh, changed. So uh, this is what we were discussing in the last class. So in today's two classes, uh, we will what is called cover all of DSP fundamentals, whatever we can. But I am planning first lecture will be on Fourier, and second will be on the Z transform. And the rest you have been asked to do the assignments. It's due by 31st of August. Please take that seriously. It's all assignment is uploaded in Google Classroom, as you know. But I saw only some of the students have joined the classroom. But anyhow, let's start. So LTI system, as you said, maybe I should use a thicker line. LTI system, as you said in the last class, so it helps us predict the output. It enables us to predict the output provided the sinusoid is given. For any random input xt, we can get the output in the time domain through a operation called convolution. If you're already revising, I hope you are in signal systems, you will be familiar with this. And we have something called the impulse response. The impulse response gives a representation. It represents the what is called how the system behaves. It gives the in a mathematical form the behavior of the system. It's also called represents the characteristics of the system, something like that. These are just fancy words, but basically you have a mathematical structure, mathematical form, or a set of numbers which help you predict the output of the system. And this set of numbers, we call it the impulse response, or if it is a function which represents it, it's the same thing. The same will go for your discrete time system. So you have a LTI system, some input, you will get an output through this convolution operation. The convolution operation is this one, and exactly or mirroring the uh, convolution operation of the continuous time system. So let's move forward. We also discussed about, we said no, that if we give a sinusoid as input, we will also get a sinusoid as output. This is called an Eigen Function. To any system, if you give a particular function, a particular signal, and the output is the same signal modified a little bit, maybe with respect to the amplitude, then we call it an Eigen Function. And the amplitude becomes the eigen value. So here we said about sinusoids, e to the power, or maybe I will write on the right hand side. We said e to the power j omega t. Now, if it turns out that any signal of the form e to the power st, where s is equal to sigma plus j omega. Sigma is a real number, omega is a real number, but this s is a complex number. Any signal of the form e to the power st, if you input to the continuous time LTI system, you will get the same output with a change in the amplitude. So that's why LTI systems are so useful, and Fourier analysis and Laplace analysis are so useful. The same thing for discrete. In discrete, we represent in polar form z to the power n, where z is a complex number. Z we represent by r e to the power j omega, where r is a radius in the complex plane, omega is the angle. So you will have r to the power n e to the power j omega n. So if you put r equal to 1, it's the Fourier uh, Fourier, what is called Fourier, what we discussed in Fourier, a simple sinusoid in discrete time. So if you put z to the power n as input, you will get z to the power n as output into a LTI discrete time LTI system, which its amplitude possibly modified. So we discussed that. So let's go forward. So when Fourier was deducing his equations, his theories as to how to represent signals in terms of sinusoids, so the first thing was he represented in term periodic signals. He found a way to deal with periodic signals, and then he or later people found a way to represent uh, aperiodic signals also in terms of sinusoids. So periodic signals, for example, you have something like this. If you have, I think, uh, electronic circuits or something labs you must have done, then you have a square wave generator, or we have a sawtooth wave generator. So these are periodic signals. So anyways, so the first representation of periodic signals is the first thing that came up. So you have a periodic signal. That's like in your electronics classes, you might have heard this square waves and sawtooth waves and all that. So you have a periodic signal with a period t naught. Then these are the two relations in terms of harmonics. You have in terms of harmonics. See, omega naught is the frequency of the periodic signal. So in terms of harmonics, you can represent the signal. Sinusoidal harmonics, you represent the signal, and these are the two equations how you get your Fourier and your inverse Fourier. So moving on now, if you think, imagine that P naught, your period goes to infinity. That's how you derive, if you have gone through your signals and systems, that's how you derive your Fourier transform. And these are the relations, and we have talked about it before last class. So what are we trying to do? We have your signal xt, we're trying to represent in terms of infinite number of sinusoids, and we give an amplitude to them. We give some kind of amplitude, a number associated with it. So I was talking here about the concept of inner product. See, how do you get your Fourier x of omega? So x of omega, you see, xt and e to the power minus j omega t. So this is called an inner product. In vectors, if we have two vectors, UW, you must have heard about this dot product, U transpose W or U dot W. When u and w are in the same direction, when they are equal, you will give the maximum value. When they are in the same direction, also you will get a very high value. Suppose, however, u is 90 degree to w, then you will get 0. If it is opposite, you will get -1. So your this inner product or dot products gives you the similarity between two vectors. In the same way, now suppose I was saying, now if these u and w were representing 2 points, but two complex vectors, okay, instead of uh, real numbers, they were representing complex numbers. Then you will have to take, instead of transpose, something called Hermitian. What is Hermitian? Hermitian is transpose and conjugate. So one of the vectors you will have to take both transpose and complex conjugate of that. So what you are seeing uh, in Fourier transform is also the same thing, but in signal form. So what we are doing is to get your x omega, you take your signal and you take actually an inner product of your signal and a sinusoid. This is given by, you will take a complex conjugate of this. That's why minus j omega t and dt. Xt you keep as it is. You take the complex conjugate of e to the power j omega t, and this is the definition of inner product in algebraic form for signals. So what you have, any xt gt signal is there. Two signals. If you take inner product, what will happen is minus infinity to infinity xt g star t dt. This is the definition of inner product. So what we are trying to do, we are trying to find the similarity of the signal and a complex sinusoid. And then you get a number x omega. And x omega, obviously, because it will be a complex number in most cases. So you will get uh, a magnitude part and a phase part. You can represent it like this. So I hope you are familiar, decently familiar with complex number and how to represent it in this form, magnitude and phase form. So I want to talk about what magnitude and phase is. So you have a sign, let's say some signal of certain frequency. This is what is phase? Phase is if you shift in time domain by some amount, then in angular terms it becomes phase. If you shift your sinusoid, instead of starting from in a normal way, sine 0 equal to 0, if you shift this signal, whatever the shift is in time domain, that becomes your, that is represented as an angle in our frequency domain. And what is magnitude? Basically, we are finding out what is the strength of this signal, how much strongly this sinusoid is present in xt, that is given by your magnitude. And what is the shift? If this signal is present in xt, what is the shift we have to do? Is it remaining with zero phase, means it's exactly as it is, or you have to shift the signal in time domain, so that finally all the sinusoids that we are summing up, they add up to give you that original signal xt. So that's what I was talking about. So now let's go back to what we are saying. Yes. So I hope this is clear. The concept of inner product. Anyhow, I will move forward. So these are the properties of Fourier transform. Many are there, lots of properties. You don't need to memorize all this. With time, as you go forward, it comes automatically to you. But what is important here is this convolution and multiplication. Maybe I will. So these are the most two important uh, properties of Fourier transform. Because of LTI system, because it is represented by convolution, they become very, and then this property, this will come very handy. Sorry, this property will come very handy during your sampling process and your Nyquist theorem. This is also very important in communication systems. But anyhow, for all signal processing cases, during sampling will require this property, and convolution obviously will require this property. These are the important things that anybody should know at any time. So, so there are many basic Fourier transforms. If you apply, you will know some of them, periodic square wave and all this. So one important thing is that we have said that this Fourier series is for periodic, but Fourier transform is for aperiodic. That is not completely true, because periodic signals also we can represent by Fourier transform, and this is how you represent it. This is an important thing to know. So if you have a periodic signal and you have your coefficients, Fourier series coefficients ak, then you can represent them by some Fourier series ak. You can represent Fourier transform of that as an infinite number of discrete impulse functions. This is the relation. So this is an important relation to know. It comes up, it becomes very useful in many cases, many scenarios. So now moving on to discrete version of Fourier series. So what we have is these periodic sequences. Instead of in the time domain, we had at the time axis was continuous. We don't have a continuous time axis now. We have just numbers, and those numbers could represent different times. So you have n equal to 0, 1, 2, 3, or minus something something, and this n equal to 0 something, it could represent some time 0. This could represent time ts, 2ts, something, based on uniform how you have sampled the signal to get your discrete time signal. But anyhow, once you have a set of numbers which are periodic sequence of numbers, then you can use your discrete Fourier series. You can use a discrete Fourier series, and these are the two relations. It's very similar to continuous Fourier series, as you can see, but there is no integration. There is no integration because it's a discrete sequence of numbers. So again, this is nothing but inner product, of a sinusoid with the signal to get your coefficients. That's the concept. The Fourier transform, again, if you think your period is infinite, you get your Fourier transform, and these are the relations. How you get, again, here it has been represented by omega, has been represented by this big omega, but in your many of your books you will see e to the power j omega, or simply even omega. But just by context you will know whether it is discrete or continuous time, whatever. So this is your signal. So again, what is happening is, it's an inner product. To get your Fourier transform representation, you take an inner product. In this case, because these are discrete numbers, sequence of numbers, you don't use integration, you use just summation. Integration and summation becomes equivalent when you have discrete set of numbers instead of continuous. So we have talked about this magnitude and phase. So magnitude and phase, if you have whatever x of omega, then you can represent as this is your magnitude and phase. If you plot x of omega as a function of omega versus omega, that is your magnitude spectrum. If you plot theta omega as versus omega, that becomes your phase spectrum. Once again, uh, all these properties I expect you to go through. You must know that in discrete signals, omega or your frequency, angular frequency, is not continuous. It has a period of 2 pi. That's an important thing to know. And once again, this relation, Fourier transform, is also applicable for periodic signals. How to do so is very similar to your uh, it's very similar to what we saw in continuous time. If you get your coefficients ak from periodic signal, Fourier series coefficients ak, then you represent it as a ak del of impulse function omega minus 2 pi k by n. 2 pi by n is basically your whatever is your period of the signal. If this is periodic with period n, then 2 pi by n is your omega naught. So it's a impulse functions located at particular specific points in the frequency axis, basically representing harmonics. So this is important to know. It comes in handy in many cases. So let's go back and come to sampling. So what are we trying to do? We have talked why we need discrete signals in the first class itself, discrete and digital signals, because we cannot store infinite number of numbers. We cannot compute infinite what is called infinite calculations. We cannot store infinite sinusoids and so on and so forth. Instead of integration, we generally in a computer do very high precision summation. So but how much precision do we need? So this is what your Nyquist theorem comes. So what we are doing is, you have a signal xt. Your xt will be this continuous signal, and we multiply with a signal sat. This sat is nothing but this impulse functions, unit impulse functions, a periodic train of impulses. It's called a periodic train of impulses, and they are separated by a distance ts. So this sat is represented like this. summation of n minus this one. So if you multiply, then you will get this. So this is what we represent now. You see 0 0, this is a sequence of numbers exactly the same. The only thing is you are saying this is your continuous time axis, this is your discrete time axis, set of numbers, an index representing those corresponding time points. That's an index, and you get the amplitude by that. So both the signals should have the same Fourier transform. We are changing the continuous time axis to a index, but both represent the same sequence of number. The in between all are zero here, but the values here are exactly the same. Both are representing the same thing. It's a way in which we are just storing the values, so to say, or representing for our convenience. So if you go through this process, if you evaluate what is Nyquist theorem, what is periodic sampling, you will find that you will find a relation. You will find that both of this will have the same Fourier spectrum. This will be a continuous time Fourier spectrum, and this will be discrete time Fourier spectrum. Both will have the same Fourier spectrum. Okay, let me do one thing. Let me write it as like this. So both will have the same Fourier spectrum, but your Fourier, this frequency axis will be different. And how are the frequency axis related? You will find there's a very important relation that your discrete time frequency axis is related by your continuous time frequency axis and your sampling period. Sometimes we represent this by and if you write 2 pi f 2 pi this one, so you can write a frequency continuous equal to frequency discrete by fs. So what will happen is, let me add a page. What you will find is this is your omega. It will be mapped to minus pi to pi. Whatever maximum frequency is in your signal, we call it a band limited signal. Only then we do sampling in the continuous domain. Omega s is nothing but 2 pi fs. What is your sampling frequency? It has to be the maximum frequency, or 2 pi fm. That maximum frequency has to be half of your sampling frequency. Only then you can convert into a discrete time signal, and you can then ideally reconvert back, at least theoretically you can get back your continuous time signal if you follow this relation. If you follow Nyquist criteria, there is something called aliasing. What is aliasing? Please go through in your assignment. But this relation This is important. You should know how continuous time Fourier transform and discrete time Fourier transform are related. In the this is the basic relation when you do sampling, convert a continuous time signal into discrete time signal. So let's see now what's next there. uh, I will take 2-3 more minutes and then we'll take a uh, break. So we have talked about LTI systems, but there is something called, even in mathematics, I'm sure you have come across differential equations in your mathematics courses. You may have forgotten, but what's the purpose of differential equations? Well, for you, electrical, electronics, computer science students, you must have solved RLC circuits. That is the best example for you. That when you solve an RLC circuit, it comes out to be a differential equation because capacitor, inductor, all those are integrations or differentiations of one variable or the other, current, voltage, all that. That is how it is related. So to find out the equations and the solutions to those circuits, the transient solutions, you have two types of solutions. One is a stable and one is a transient. What is meant by stable and transient? See, this circuit, let's put RC. Stable means if you keep it on, you know no current is going to flow. This is stable. But initially, initially it was not like this. For example, you disconnect this, maybe there is a switch. So if this was some V naught, no current is flowing, V naught, it will be stored. The capacitor is storing a voltage V naught. Now you disconnect, and then reconnect it. Okay, and then reconnect it. So then during this process, there will be some current flow, something will happen. Generally, the current should not flow, but some current will flow and it will finally die down. Some current will flow, some I naught will be there, and then e to the power minus some with time t by tau. If you remember, tau is some constant of the circuit and all that. So to know about the characteristics of the system, this time constant, all these things, you need differential equation. Now these are very small circuits. Imagine your motherboard in your computer. So this is why we need differential equation. In case of speech, now I will tell your this is not related to electrical engineering, but to acoustics. So your people who study in physics in class 11, 12, you must have studied viscosity and fluid dynamics a little bit. But in civil mechanical engineering and other, there is a very full-fledged subject on that, viscosity, fluid dynamics, and all that. So the air that is coming out from your lungs and a speech, it is coming out through a tube, and it is also a fluid. It has viscosity and all that. So that comes out to be a very hefty differential equation. People who have analyzed that, done anatomical studies and all that. So from that equation, we use signal processing techniques, Laplace transform and all, to get some hold of, give a easy mathematical way of analyzing our speech system, speech production system. So that is where differential equations and differential equations comes into practice everywhere around us. You will find that. I'm just giving you examples that you have already encountered in life. So now these coefficients, they are very important, and they give you a lot of idea about what the system is. But as you can see, this is very difficult. A huge equation it will come. So we don't go. We engineers generally look for shortcuts. Everybody to make our lives easier. If we could convert it into a algebraic equation instead of a differential equation, then our lives will be easier. We could analyze it easier. This is where Laplace and Z transform comes. The main goal is to convert these differential and difference equations into a algebraic form, into some polynomial form, x squared, x cube, and all that. Those are we find it easier to solve, easier to analyze. So that's what we'll discuss in the next class. Uh, so we'll take a little bit of a break, 10 minutes break at 11. Let's come back. 10:50 it is now. Let's come back at 11. So linear constant coefficient differential and difference equations. These are an imperative part of any natural system, and even our whatever systems we implement and design. Sometimes, or in many cases, we design the system in frequency domain because it makes our life easier. But obviously, we will represent it again in the time domain. Whatever we do in the system frequency domain, whatever system we design, we again represented that in the time domain, and then through convolution we achieve our task. That's how things are implemented. So what I was saying is, if you have where is it, just a minute. So let's say you have a system. What is hz, what is hn, we will know. uh, I hope you at least are familiar or know the names of Laplace and Z. But this is an impulse response of the system, and this is what is called its corresponding Z transfer or transfer function. So you have a signal and you get an output. Now, obviously, you are when you are designing, or even if it is a natural system, it is Z equal to R dt over j omega, if you recall. And when R equal to 1, that's when it becomes a Fourier transform. That's when it becomes a Fourier transform. So it makes our life easier to analyze in terms of Z transform instead of direct Fourier transform itself. Why? That's a very good question. See, all systems, whatever the characteristics of the system, you will find generally you will have some sinusoid type characteristics, and also some decaying or increasing characteristics. If it's increasing, we call it unstable system. And this decaying, it is a stable system. Generally, something like this or something like that will represent the system. So there are some very good videos I have found on YouTube. I will share with them. Go through them. It will give you very good intuition. But again, you have to browse through your books and revisit those concepts. But in Fourier, you are taking what is called inner product of a sinusoid, complex sinusoid, and your signal. In Z transform, you are taking the inner product between a decaying and increasing sinusoid or increasing sinusoid. So sorry, I am representing continuous time here, but it's the same for e to the power j omega n, discrete time also. So uh, xn z to the power n, where z equal to r e to the power j omega. So this becomes r to the power n e to the power j omega n. So it is a sinusoid and a, depending on this parameter r, if r is greater than 1, it's increasing. If r is less than 1, it's decreasing. If r is 1, it's a classic Fourier transform. So we're trying to find out basically increasing and decaying sinusoids. So you must have in your physics in class 11, 12, or maybe even in control systems, if you had a course, damping oscillations when a system is under damped, over damped, and all that. So when a spring, for example, is under damped, over damped, those kind of situations. So those represent this, those kind of damping, whatever nomenclature you use, whatever names you use, those phenomena are present in all systems. So we are trying to find out basically in Z transform that not only just pure sinusoid, but increasing and decaying sinusoids. Are there anything in those kind of signals are present in our system and our signal? So you have, so basically your impulse response we represent in terms of Z transform, and in case of continuous time signals it's Laplace transform, and we get our output. So why I am saying all this is because Z transform makes it very easy to analyze difference and differential equation, Laplace and Z transform. So this equation, for example, is all these difference and differential equations. It will, for example, if you take a Laplace transform of this, let's say, let's go below Laplace transform, which is equivalent to Z transform. All your ddt of something to the power n will become nothing but s to the power n. Just a minute. Some n something will become your s to the power n x of s. It becomes an algebraic equation, polynomial equation, which is easy to solve. Similarly, in your Z transform, all x n minus some 1 n minus 2 n minus n will become z to the power or plus n or minus n, whatever, z to the power minus n x of z. So this form makes it easy to analyze your equation and also easy to design, analyze your system, and also and also makes it easy to design your systems. So now, so let's go ahead straight with what a Laplace and Z transform is. As I said, see what's happening here is the inner product between this signal and e to the power st, a signal ht. It could be any signal xt, anything, and this increasing or decaying sinusoid, e to the power minus st, where s equal to sigma plus j omega. So depending on the value of sigma, it will be increasing or decreasing, and e to the power minus, uh, so it will be minus sigma t j omega t. So it's an inner product between the signal and an increasing or decreasing sinusoid. So that's what a Laplace transform is. In the same way, Z transform is the inner product between your signal Hn and a complex sinusoid. But depending on the value of R, it will be increasing or decreasing. So this is the basic idea behind why we use Z and Laplace transform. Now this, in case of Laplace, the sigma, the value sigma, and in case of Z, the value of R, that will determine in what range, what region, or what are the values of R or values of sigma in which you can get a mathematical convergent solution. In other words, just a minute. Whether this exists or not, whether you can find a non-infinite solution to this, or rather a finite solution to this, depends on the value of R here. There are a range of values of R for which this signal will have a Z transform. Same case for Laplace transform. And this region is known as the region of convergence. So I will talk about regions of convergence. Just a minute. Yes, regions of convergence. So maybe I will put a slide. Yes. So yeah. So you have your x of n and x of z. It's the inner product between xn and zn. Anything? Someone pinged, I think something was there. No. Okay. So inner product between xn and zn. So for certain values, z equal to r e to the power j omega, certain values of r, which means modulus of z, certain values of r, this certain regions in which this integration will be valid, will get a finite value, and this is called region of convergence. Now why does Z transform and Laplace transform are very useful is that they give rise to a form which we call a pole zero form. They give rise to a formulation once you evaluate the Z transform and something, Z transform or Laplace transform. You can represent it in a rational form or a pole zero form. So xz, let me erase this. Just a minute. Let's say this. You have x of z. You can represent it in a rational form of factors. Some z minus z1, z minus z2, z minus z3, z minus z4, z minus z5, z minus z6, something like that. So when z equal to z1, obviously the Laplace transform exists, and but the value goes to 0. That's fine. So Laplace transform exists in those regions. But when z equal to z4 or z5 or z6, the Laplace, the Z transform, sorry, not the Laplace transform, the Z transform, it does not exist. It goes to infinity. It is undefined, basically. So these points, you can plot. These are called the poles. Is Z4, Z5, Z6. These are called the poles. Whatever you get, whatever are the values for which you get zeros, those the Laplace transform goes to, those are called zeros. It could be something, whatever. So these are called zeros, Z1, Z2, Z3. Now there are two very important cases that you should look into. What is the effect of having conjugate poles and real poles? Why conjugate? Uh, See, what will happen is if you convert uh, this Z transform, for example, I will erase this. If you convert this Z transform, suppose you have 1 by this Z minus Z1 star, Z minus Z1. If it is not complex conjugate, your coefficients in the time domain will not be real. So that is why if you have for real signals, if you have a pole somewhere in the complex plane, then you will always have another uh, pole complex conjugate of it. If it is in the real line, there is no issue. You don't need to have this one. So my previous diagram, it was not very accurate. I was just showing what are poles and zeros. But remember, for real signals, when we are because we are dealing with real signals, you will always have complex conjugate poles. And if it is under real line, it's there is no need for that. But there could be multiple poles uh, at the same location. You can have poles of multiplicity, many orders of multiplicity. We call the term multiplicity. So So you could have some z minus z naught to the power n. So that means there are n poles there at z naught. Let's say this is z naught. There are n poles there. A similar case holds true for zeros as well. You'll have conjugate zeros and zeros of multiplicity many orders. So that's how it is. So let's go then to the next slide, the properties of Z transform. But before that, okay, let me do one thing. I want you, where is it? Yes. There are some really good visualizations on YouTube by some academicians and researchers. I'm sharing these 3 videos just like previously. Go through them. It will help you you clear your doubts or make it easier for you to understand and revise or recollect back whatever you had learned in signals and systems. So just a minute. So in these 3 videos, please go through them. Yeah. So please go through these videos. It will help you in your assignments and help you to recollect all your signals and systems and Z transform. And other videos also I had shared before. Hopefully you have gone through them and hopefully they have helped you. So coming back, so let's that was the only reason why this slide was open. Yeah, okay. So coming back now, yeah. So we need to talk a little bit about this properties of ROC. Properties of ROC. So if you have a signal, by the locations of their poles and zeros, you can infer a lot of information about the signal. So if all the poles, this is the unit circle where r equal to 1. If all the poles are inside the unit circle and your signal is right-sided, what does it mean to be right-sided? So there is some number, all to the left of those numbers, that index, there is some index and not to the left of that, the signal does not exist, means all are zero values. This is called a right-sided signal. If your signal is right-sided and all your poles are inside the unit circle, then what will happen is your ROC will also be outwards of those poles. Remember, ROC cannot include any poles. The Z transform will become infinite at the pole. So ROC cannot include poles. But if your signal is right-sided, this is also called a causal signal. The signal is right-sided, also called a causal signal, and your poles are inside the unit circle, then your first of all that ROC will be outwards of the largest pole, and it will also include the unit circle. It also includes the unit circle. If it includes the unit circle, what happens? Z equal to R e to the power j omega. R equal to 1, then that means Z equal to e to the power j omega. That means Z transform at the unit circle, your Z transform is the same as your Fourier transform. In other words, your Fourier transform is guaranteed to exist. Your Fourier transform exists if your signal is right-sided or causal and all your poles are inside the unit circle. If all your poles are inside the unit circle, the ROC will be outwards, and it will obviously the ROC will also include the unit circle, and hence the Fourier transform will also exist. I did not mention before, in order for Fourier transform to exist, there are a set of conditions called Dirichlet conditions. But this is guarantee. Okay, this is a guarantee condition or sufficient condition. Okay, Fourier transform can also exist if these Dirichlet conditions are not satisfied. Okay, so one of the principal thing in Dirichlet condition is, in case of continuous time, let's talk about discrete time. It's the same, but this should be finite. Yes, all the the magnitude of the samples of the signal, the entire signal, if you sum up, it should have a finite value. It cannot go to infinity. So it is called finitely summable. So if it's finitely summable, then it is guaranteed that Fourier transform exists. This is also represents a stable signal. This is also the definition of stability. So now, even if Dirichlet condition does not exist, of course, Fourier transform can exist. But if Dirichlet condition is satisfied, it is guaranteed. That means it is a sufficient condition. It is not a necessary condition. It's just sufficient. Dirichlet condition uh, is being honored, or it being followed by the signal, then Fourier transform is guaranteed. But for example, you have this unit step function n equal to 0 to infinity. Less than n equal to 0 does not exist, but it exists for infinite time till infinity. It's one unit step function. You must have, I think you should recall this function. This does not follow Dirichlet condition, but it still has Fourier transform. But in most cases, or general signals, we cannot, we don't have any mathematical representation. So Dirichlet condition is necessary so that Fourier transform exists. Generally, that is what happens. There are also signals in which it does not follow. Mathematical signals are there, but Fourier transform exists. But in most cases, generic cases, Dirichlet conditions are what we check for Fourier transform to exist. So, going to the previous slide. So, if your poles are inside the unit circle, then and your signal is causal, right-handed, then your Fourier transform will also exist indirectly. It means that. So let's go about other some simple examples. So this is one primary thing that you should know, but there are other simple things that you can infer from Dirichlet. Sorry, this pole zero plot. Let's add another page. This is your unit circle. Now, just as it's right-handed, a signal could also be some left-handed signal or anti-causal. It's also called anti-causal or non-causal. And let's say your poles are here inside the unit circle. So your ROC will be, ROC never includes the poles, but inwards. Accepting z equal to 0, that you have to check. That is one condition. Always you have to check z equal to 0 and z equal to infinity, whether ROC includes that or not. But otherwise, it will be except those 2 points. Those two points you have to. What will happen is it will be anti-causal. Sorry, it will be inwards. If your signal is anti-causal or left-handed, left-sided, left-handed, it will be inwards. Now, suppose those poles were outside the unit circle. Then what will happen? Then that will also include your unit circle. That means the Fourier transform exists. Now, in both these cases, uh, you see the entire z plane is not there, only a strip is there. Okay, only a part of the z plane or imaginary or polar plane is there, whereas z transform exists. Sometimes Fourier will also exist if if the ROC includes a unit circle. However, if your signal is finite, if your signal does not have any infinite values and it is a finite duration, some numbers, some 100 numbers, 20 numbers, whatever, finite duration is a finite duration signal. Then obviously Z transform is going to exist for the entire Z plane, except you have to check for Z equal to 0, Z equal to infinity, whether they exist at those points. So these are the things you need to know, you need to brush up. Again, there is a case where it is a two-sided signal or it is the infinite duration. Yeah. Now, if your signal is of infinite duration, this is a finite duration. But if it is infinite duration and two-sided infinite duration. I mean, we saw one uh, right-sided and left-sided. Those were also infinite, but on one side they did not have any values. But if your signal is towards minus infinity and towards plus infinity, both sided, and then your Z transform is most likely, is not most likely, it will always be a strip between some poles. A strip between some poles. If this strip includes a unit circle, then your signal, your Fourier transform exists, your signal is stable, and so on. For example, let's a very simple example. Suppose your signal is like this, e to the power minus, let's say, 0.5 t. Let's say xt equal to this one. It's going to, oh, okay, let me put xn. Okay, it's more or less the same, xn. So this is one, then, but it is decreasing. Again, it is decreasing that side. So this signal, it strip the, see, you can see it is a stable signal. It will die out, even though it is infinite duration, it will die out. So this signal, if you take the Z transform, it should, the stable signal, it should also include the unit circle and Fourier transform exist. But other signals, infinite duration, may not exist. The Fourier transform may not exist. So these concepts of how poles uh, play a significant factor in analyzing systems, signals, and thereby systems. You should know that signals and systems are interchangeable things. When you say yn equal to xn convolution hn, you can also change it into hn xn. So I am taking here just for illustrating as xn, but Z transform, basically we are trying to find out the characteristics from of the impulse response. The impulse response that you get, hn, we represent in terms of system transfer function, which we call hz. We determine the poles and zeros and try to find out the behavior. So behavior, and analyze the system in the Z transform domain. So now these are the various many properties of Z transform. Just go through them again. Convolution, very important. Easy, the same, almost the same as your Fourier. That delay, what happens when you delay the signal? As I said, it turns out to be a polynomial of polynomial form. So these are some very basic things that you should be in your fingertips. Rest are, obviously you cannot memorize everything, but this should be in your fingertips. And these are some standard functions where Z transform you should be aware of. This one basically what is a to the power n un. Depending on the value of a, it is a increasing or decreasing signal. So it's a very standard 1 by 1 minus az inverse, where ROC is greater than the value of a, whatever is your a value, modulus of a. So please revise all these concepts. That's what I will say. There is a very important thing here. Sorry. In case of sinusoids, so these are the Z transforms of sinusoids. I will just go through an important illustration of why sinusoids are so important in Z transform analysis. Okay. Before that, let me, yeah. So now let me cover this, and then maybe in 4 or 5 minutes I'll talk about that. So you have this. You have an LTI system from where you can get an output if you put an input xn, and the impulse response if you know hn. So in based on this convolution property, you can represent it in simple multiplicative terms, and your transfer function becomes xz equal to output of the z transform of output divided by z transform of input. So this transfer function, that's why it relates how output will change with respect to the input. So, and it makes your analysis easy. It also shows why, in for example, I said about complex conjugate poles and complex conjugate zeros. If you don't have complex conjugate poles or zeros, this final equation is that you will get if you put it in terms of your time domain equation. These coefficients that you will get, those will not be real. So that's why we need those poles to be and zeros to be complex conjugate, or simply lie on the real line of multiple multiplicities. So I was talking about why. Just simply go now and give a illustration of what happens if there are, sorry, if there are real poles. So real poles. Let's imagine there is a real pole somewhere, and let's just imagine z equal to 1 by z minus some value a. So at a there is a pole. So if you now you can say this is z by z minus a by z inverse. Now if you go back here, sorry, what is z by z minus a? A to the power n un. So you'll find it will be into, it will be a to the power n un. And if you go by properties of Z transform, then Z inverse means delaying the signal by unity. Z to the power minus 2 will be by delaying 2 times minus 2. So like that. So if you see what is happening is, depending on this value of A, your signal is either increasing or decreasing. So it starts from n equal to 1. Depending on the value of A, it will either increase or it will decrease. So a real pole represents a simply exponential, is a discrete exponential. These are called discrete exponentials. So it simply represents an increasing and decreasing trend, non-linear increasing and decreasing, just like e to the power something exponential function. It is just increasing or decreasing trend. We generally want decreasing trend. That means the system will be stable. The system will be stable. So now let's say what will happen to complex conjugate poles. Okay, let's say this is a unit circle. Okay, and there is a complex conjugate pole. Okay, so 1 by z minus a Z minus A star. So magnitude remains same. If A equal to, let's say, some R naught e to the power j omega naught. So this is omega naught, let's say, and this length is R naught. What will happen to A star? Mr. R e to the power minus j omega naught. That means this is minus omega naught. That's it. Now we know how to get if you put z equal to e to the power j omega, we get the Fourier transform I have told you. So let's try to get the Fourier transform here. So z, if you put z e to the power z equal to e to the power j omega, so this is the line. This is the depending on the value of omega, if you will get the Fourier transform uh, value for that particular frequency. Now let's imagine when omega equal to omega 1. When omega equal to omega 1, what will happen? See, this is what z minus a is the distance. So let's say omega equal to omega naught, not omega equal to z minus a is this distance, and z minus a star is this distance. So when omega equal to omega naught, if you take the frequency response or what you call the Fourier transform, see this distance is so low, it will become very high. H e to the power j omega h e to the power this e to the power, sorry, j omega naught, it will become very high. Similarly, e to the power minus j omega naught also, it will become very high. So if you have a Fourier transform plot, if you do, you will find that at omega naught, very high value. Similarly, minus omega naught. And this happens when your this R, this R naught, this R naught is very, very near to 1. If R naught is becoming very, very close to this unit circle, you see this distance is very low. And hz at that h of e to the power j omega naught, it will go to nearly very high values. So then we call such a system as a resonator. We call such a system as a resonator. And these frequencies are called resonant frequencies. So that's all. I think I've crossed the today's almost it's the time is over. I think above time. So I will stop the lecture. There will be no more revision of DSP because Thursday is a holiday. So I did not know. I wanted to, but there cannot be. There is not much time. Please revise signals and systems, and then please submit your assignments. From next week, we will start speech processing. So hope that's all right. Bye.